Hello everyone. So today we're going to talk about conversions, and we're going to do some really simple examples in the hopes that we get everyone at the same point in terms of being able to do conversions. So I'm going to ask you to pause the video and do some of these as we go. So the first one is convert 6 tablespoons to cups. And the choices are, let's pretend it's a multiple choice test. You can have one answer be 0.67 cups, next answer 0.15 cups, then half a cup, and the last answer 0.375 cups. And now if you've gotten to know how I do things a little bit, you might be wondering, don't we need more information? And you're absolutely right. If we did this, have a show of hands, I don't think very many people could do this one without the almighty Google machine. And there's no way I could do this conversion without Googling and knowing how many tablespoons are in a cup. So I don't actually know that. I just Googled it. Turns out there's 16 tablespoons in 1 cup. I like to cook a lot. I really wish that everything was in metric because it's a pain in the butt. So if you're interested, you can do this. Let's see, 16 tablespoons in a cup. We got 6 tablespoons, so you could go 6 over 16 and figure out that that's the right answer. And if you can do that, you've got good proportional reasoning. You're going to find this section fairly simple. But let's do another one before we get started with how we're going to do it in chemistry in a more systematic way. And that is, let's convert 57 milliliters to liters. And if you have our choices, let's put the choices down. 570 liters, 0.057 liters, 0.57 liters, and 4 is none of these. So just to give you a heads up on my multiple choice tests anyway, and so I'm doing this in 2 ways, and so I'll try and make sure that I scroll it up so that people who like it on YouTube can see it too if I goof and miss it a little bit. The none of these choice on those evil multiple choice tests, it's never none of these. I mean, it's very rarely none of these. So on a multiple choice test, the only time you would ever put none of these is if you're 100% certain. So when we do this, a lot of you would remember how many milliliters in a liter. I'm guessing when I've done this with the class before with these, we do really well on one like this where it's in metric system, even though we're maybe more familiar with the English units of miles and things like that. So anyway, you move your decimal place one way or the other, and it turns out that this is the right answer, 0.057 liters. But here's the deal, even if you know that and you can do that, you want a systematic way to do it on tests. It's pretty easy, especially if we're getting in, there's 2 things that makes chemistry hard. Unfamiliar things and numbers that are unfamiliar, like scientific notation, we're out 10 to the minus 7th or something. And then it just makes it easier to make mistakes and move the decimal place the wrong way. So what you want to do is you want to build in procedures so that you don't make any mistakes. Okay, a systematic way of doing it. Because especially under the pressure of a test, time pressure, everything else, pretty easy. Maybe if it wasn't liters and milliliters, maybe it's somewhere else out there that you're a little less familiar with. It's easy to go the wrong way and actually make a mistake on that. So what we want is a nice systematic method of doing conversions and getting the right answer. So let's write that out. Systematic method for conversions. And again here, I'm going to show you two different ways, and most people won't need all of this detail, but I like to do it very thoroughly at first, just so that everyone can do these and is at the same place. And then when we go on to stoichiometry and things get a little bit more difficult in chapters 3 and 4, then everyone's prepared for that. You can solve a lot of problems just using conversion factors. Most of chemistry problems can be done just by paying attention to the units and doing conversions. So the systematic method, here's the example we're going to do. Let's convert 180 pounds to kilograms. And I always give you conversion factors, except for the metric prefixes that you're asked to know. So we would look it up on Google or in front of the test and find out that 1 kilogram is equal to 2.205 pounds. All right, so in algebra class, and you work on proportional reasoning, and hopefully you know how to work with ratios. So I'm going to first show the ratio method and then show you another way of doing it that's going to be really powerful. So the ratio method is to look at this and say, and I apologize if I'm not doing this like you would have learned it in math class. I took math, 40 years ago. And the way that we would do it is this is to that as this is to that, right? You set up a ratio, 12 inches in a foot. So if I have 36 inches, how many feet is that? And you put your X in the one that you don't know. So I'll just go 1 kilogram is to 2.205 pounds and set that ratio equal to, let's see, we have 100, so it's X kilograms, that's what we're trying to solve for, and 180 pounds. And that way we can figure out how much I weigh in kilograms. So let me find my calculator, plug that in. So when you solve for this, I hear a lot of students always talking about you learn all these different ways of solving things in math class, and you don't need all that, right? If you're solving for X, you're just multiplying through by 180. You don't have to cross multiply or anything like that, right? You just multiply both sides times 180 pounds, 180 pounds, pounds cancel, that cancels. And so we have 180 divided by 2.205. Let's see what we get. And I get 81.63 kilograms. All right, so that's the ratio method. It's a really powerful method. You're just applying proportional reasoning, and you can solve a lot of things that way. And it's perfectly fine to start your conversions in chemistry using the ratio method. If you're comfortable with it from algebra class, you can solve a lot of conversions that way. But what if you have to convert something where you have 2 or 3 or 4 different conversion factors? It becomes kind of cumbersome. You have to solve for each one in between. So there's another method that is really powerful that I want to show you. And I know I usually would ask the class how many people raise your hand if you've seen this, because most students who took chemistry would have used something like this. So I call it the factor label method. There's other names for it. That's just the name that sticks in my head. And in the factor label method, what we're going to do is always multiply by 1. If you multiply something by 1, you haven't changed it, so you haven't messed anything up. And we're just going to look at the units until we get to the right units. So this is going to be excruciatingly long. We already know how to solve it, right? Because we just did it with the ratio method, so we know the answer. But I want to show you how to get conversion factors, right? And where this comes from, so that when we do get the more difficult stuff, hopefully it'll make sense. So 1 kilogram is the same amount of mass as 2.205 pounds. And we can make 2 different conversion factors out of that. So just manipulate, I'm going to misspeak, I'm not going to re-record it. Manipulating this, I can divide by 2.205 pounds, 2.205 pounds, and then now this is equal to 1, right? And so we've just made a conversion factor. 1 kilogram divided by 2.205 pounds is equal to 1. And we can multiply that by something and not change anything. We could have gone the other way, right? By the same token, we have 2.205 pounds divided by 1 kilogram is equal to 1. So those are our 2 conversion factors that we can use. And so any equality, 12 inches in a foot, whatever it happens to be, you have 2 different conversion factors that you can use. And what you do is you just use the one that gives you the right units. So very key in doing conversions. Always start with the given value. Hopefully you can read that with the given value. So whatever you're given to convert, you write that down first. We want to go from 180 pounds, pounds, and get that to kilograms. So now I look at my conversion factors, right? We're going to treat the units just like their numbers. We can treat them algebraically. Why did my K get goofy looking there? Terrible. 1 kilogram. So just treat the units like their numbers and cancel them out just like you would in algebra. So if we want to get from pounds to kilograms, we need kilograms to be in the numerator. So I'm going to use the top conversion factor. 1 kilogram is 2.205 pounds, and I'm going to multiply by that, and the pounds cancels, and I do that, and I forget what exactly the number worked out to be, 81.63. And that's our answer. Now, does that seem better than the ratio method yet? Probably not, right? If it's a one-stepper and the ratio method makes sense to you because you get proportional reasoning, that's fine. But what's powerful about this is, what if you have to convert through 2, 3, 4 steps in a stoichiometry problem? So later on, when we're going from grams to moles, moles to moles, moles to grams, and back again, right? And you can string those all together in a long, and as long as your units are canceling, and as long as you get the right units when you're done, even if you go in circles, which sometimes happens, as long as you're in the right units when you're done, you got the right answer, and you should have confidence in that. So the factor label method is a really powerful method, and you want to work on being able to do that.